Tony Fry. I work at the National Physical Laboratory in Teddington. Should we go to the next slide, please? So for those who don't know NPL, we're the UK's National Measurement Institute. Our main focus is on metrology and metrological solutions to support industry. Ultimately, we are aiming to provide confidence and trust in technology and data. With regards to materials, one route to this is through measurement methods to provide materials assurance. Next slide, please. The properties of a material are intrinsically linked to both the processing and the microstructure. And the properties, microstructure, and processing ultimately govern the long-term performance of the material. So what we need to be able to give materials assurance for our industrial links and customers is to have the right characterization tools and tests to do that. If you just move on one click. And what we're aiming to do is to actually have methods of measurement and testing that are both reliable and valid, so you get the right answer with the least amount of uncertainty. Next slide. The focus for this presentation is very much on reliable measurements of defects of the final part, as opposed to what we've heard in the previous two presentations, focusing on the powder. I'm going to focus on the final part and the influence that the defects have on the mechanical properties. That being said, the focus really is on detecting and sizing those defects. So the method I'm going to talk about is XCT, and the reason why we need that is to help with the future digitalization and development of materials through the use of the digital twin concept. So next slide, please. If we start with conventional methods, so metallographic imaging has been around for many years. It can be applied to powders or parts, the final component. So the video there is of the powder. It's been recycled powder, and the images on the middle and the left is an AM part, where you can see we both have macroscopic defects and microscopic defects in the form of porosity. Current optical methods are reliant on an operator looking at the sample and intervening where there are issues of contamination or poor quality control. That has a number of implicit problems with it, in that it has generally poor repeatability and it's labor intensive. More recently, we've been looking at large area scanning coupled with EDX measurements. So the video you see there, for example, is a wide area scan of powder. We can link that now with machine learning and AI to identify automatically within the SEM regions of interest, which the user can then come back to and take a closer look at, thereby saving time and hopefully having a more repeatable method. Next slide, please. This is the kind of data we can get from those types of measurements. So you have the distribution of pore size on the left as a function of its frequency, which is important when we come on to looking at incorporating those defects and pores in any mechanical models that we might use in a digital twin. We can also use EDX, energy dispersive X-ray spectroscopy, to look for contamination within the powder. And the example given here is a titanium powder, which had been recycled, and we found contamination of iron and chrome in there. Next slide. One of the other things we can do within the SEM, just touching on it briefly, is use electron backscatter diffraction. We can combine that with in situ mechanical tests within the SEM and look at things like the deformation mechanisms within the parts, the development of shear bands, dislocations. We can measure grain size, the texture within the material, so how the manufacturing process is going to affect the anisotropy of the properties. Next slide. But ultimately, what I want to focus on now is how we need to improve the measurements of these internal defects, so that we can implement them into a digital model, so that we can predict the mechanical properties of the material and the long-term performance, such that we can help with materials development and materials assurance. This is particularly important if you consider testing across the length scales. So the second image on the left there shows a standard fatigue sample compared to a miniature test piece, the matchstick in the middle, which can be removed from a thin wall component such as a blade there. And then going even to a higher scale, we can now do tests within the SEM using cantilever beams or pillar compression tests to measure and characterize particular features of a component or a part. So as we're testing across these different length scales, it's important to get a representative volume element that we can implement and put into the model. The model itself would need to have an accurate kind of description of both the pore size, the defect size, and its distribution within that volume element. Now to do that, we use XCT. So next slide, please. I think it's widely viewed that XCT is the gold standard of non-destructive evaluation for AM parts. It's not a cheap or quick technique, but it is one that does give you a kind of level of information that you need. But it does need calibrating. And to do that, we've been developing a sphere phantom. These are effectively a small container as shown in the image there, with a number of highly machined balls of different materials that are packed into that container. It's cheap to produce, it's easy to register it, and you can test a number of sources of error or uncertainty in XCT measurements using that phantom. Next slide. So this is the process that we've been going through. You get your projected image shown on the left. That's then reconstructed, and then typically people use a thresholding technique to identify the edges of the different components within there, the balls. Generally, people use an ISO 50/50, so that's looking at the threshold value that is 50% of the intensity. And then you identify the surfaces, and then you can do your reconstruction. And then in terms of the calibration, you would measure the center to center distance between the different balls. So we've been comparing different techniques for doing that kind of surface determination, starting with a sphere fitting, then moving on to a spheroid fitting, and then more recently actually not using thresholding at all, but looking at how the rate of change in the grayscale varies. So the next few slides will compare the results for those. So next slide, please. If we focus on the graph on the right-hand side there, the blue data points, the blue box profiles, they show the results and the scatter in the results using a global thresholding value. You'll see from the key there, we have balls of zirconia, alumina, silicon nitride, and silicon carbide. And as we move from left to right on that plot, we're moving into different materials. And you can see, so the ball that's 3 millimeters diameter, the silicon nitride, has a much higher uncertainty or error in its diameter determination than some of the other materials. And this can be in the positive direction, as in the silicon nitride, or in a negative direction, as in the case of the silicon carbide. If we move away from a global thresholding technique and actually treat each sphere individually and optimize on each sphere, you can see that the actual error in the diameter determination reduces, and that's the red data shown in that plot. Next slide, please. But if we move away from the thresholding technique and actually look at using a spheroid and detecting the surface of the spheroid based on the rate of change of grayscale in the whole volume, we have a great reduction in the scatter for each ball diameter, each material, which is shown on the graph there in the green data points. So we've got a reduction in scatter, effectively reducing our uncertainty in the measurement. And these kind of plots will enable us to calibrate our XCT data to get a much higher accuracy in dimensional measurements, both of surfaces and of defects or cracks or things like kissing bond issues. Next slide, please. This is quite a complex slide, but what I want you to focus on is the two plots in the center. So what this shows is how we can use this phantom to actually calibrate the whole of the imaging plate of the XCT machine. So the two plots in the center there show the variation in the diameter as a function of position in the Z direction of that phantom. You can see as we're going towards the top of the imaging plate and the bottom of the imaging plate, because of the cone beam effect, we have higher errors in our measurements of the XCT data. So this phantom would enable us now to calibrate those errors out, to calibrate out the beam cone effect. Next slide, please. Okay, I think that takes me to my conclusion. Materials assurance for additive manufacturing, it requires accurate, repeatable, low cost and rapid characterization methods. The measurement of the microstructural defects, we can do that, not just us, but the universities and industry can do it now in 2D and in 3 dimensionals. With the move to digitalization, we're going to require accurate data to support digital twinning and digital tools that should make materials development, materials characterization much faster and much easier. And what I hope I've done here is demonstrated how NPL is helping to improve XCT measurements, to give that improved gold standard for NDE measurements of AM parts to facilitate the use of models and the digital twinning as we move forward. Thank you.